You've been learning a lot about solutions and the different ways in which they form. Some of the terms are related to their concentration, like saturation, whether they're saturated, unsaturated, or supersaturated. You've also learned a little bit about how to read and interpret a solubility curve to determine what kind of solution you have, as well as the amount of solute dissolved in a 100 gram sample of water at different temperatures. So you've learned a lot about solutions already, but we haven't got a lot into determining and discussing the concentration of a solution, which is a really important fact for a solution. What's the concentration of it? And there's lots of ways to express concentration. We can do it qualitatively. We've kind of already started to use those words. When we use words like saturated or unsaturated, we're kind of alluding to the idea that a solution can have a lot of solute in a particular amount of solvent, or just a little bit of solute dissolved into a particular amount of solvent. And so we have concentrated solutions and we have dilute solutions. Those are pretty qualitative terms in that they don't really have numbers in them. They're very comparative. Concentrated is only concentrated compared to something that's more diluted. So something that's diluted in one situation might be concentrated compared to an even more diluted solution. So it's a long way of saying that we need a more numerical, quantitative way to describe how a solution compares to another. And something like molarity is that primary way that we go about doing that. So molarity is something we've already talked a little bit about when we talked about stoichiometry back in a previous unit. And molarity is described as the number of moles of solute divided by the number of liters of solution. So in this goofy little picture here, you see there are two fuzzy little moles in a 1 liter beaker. So that would be described as 2 moles per liter. Well, that's kind of the idea. How many moles divided by how many liters? So we take the number of moles of solute that are in the solution, and we divide that by the volume of the solution in liters to find molarity, as you can see here in this equation. That equation's got 3 parts then: molarity, moles, and liters. And we can find any one of those 3 if we know the other 2. However, there are 2 more sort of extensions off of that equation that are actually quite important, because we can't go into the lab and measure moles. We can't measure moles. We can measure things and convert to moles. And so one of the most important things to be able to do to work with the molarity of a solution is to be able to measure the grams of solute that have been dissolved into the solution and convert those grams to moles. So along the red arrow there, we have conversion from grams to moles of solute. We could also go back to grams of solute from moles. The way that that's important, and again, is if we're in the lab and we're trying to prepare a solution, we can't measure out moles, so we would instead convert the amount that we need from moles into grams, and we'd be able to go measure that out on a balance and be all set. Liters of solution also, we can convert that. We can go back and forth pretty easily between liters and milliliters, simply a metric system conversion. And the reason that that's so important is because we typically don't work with multiple liters of solution in the lab. A lot of times we don't even work with a whole liter. Sometimes we work with just a fraction of a liter. And so sometimes then we'll be measuring, say, 200 milliliters or 450 milliliters instead of liters. We can go back and forth relatively easily between liters and milliliters. So there's sort of 2 extensions there in green that require a conversion between units, between moles and grams for the solute, or between liters and milliliters for the solution. So that equation, with its sort of 5 parts, the 3 main parts in black, and then the 2 sort of extended parts in green, is the only tool really that you'll need to solve the questions on the assignment that you've been given. And it'll be the one that we'll use to work through the problems together here, several examples from the assignment that you've been given as well. So I'm going to switch over to that assignment, and we'll work through a few examples on there together, try to show you a good variety of the problems that are there, and a couple of skills or tools to get you through those problems. So let's switch over to the assignment now, and we'll work on a few of those together. So here you can see the assignment that we gave you to work on, and the questions that you were given. There are something like 15 or so questions on here, 14 or 15. I'm going to work through, looks like about 6 of these, and just to kind of do a variety of different problems, we'll work through about 6 of them. If you kind of get the hang of these sooner than that, by all means, stop listening to me and go work on them yourself. Your basic job is going to be to listen to as many of these as you need or want to listen to, and then complete the rest of the problems on the assignment on your own and get those turned in by the due date. Okay, that's the idea. So we're going to work on the first one first. I've got the equation here for molarity off to the side so that we can use it to relate the information that we're given to the parts of the molarity calculation here in the equation that you just wrote down in your notes, hopefully. And there it is. If you need to pause it and put that in your notes, that's a good tool to have there, so that we've got all the different possible places to jump into this problem, the thing that we're trying to solve for, so we have a method to get there. This question wants to know, what is the molarity? So what is the molarity? In other words, we're gonna be solving for this right here. Well, what'd they give us? This question says seawater contains 28 grams of NaCl. 28 grams of NaCl, that's 28 grams of salt. That's right up here. So we have 28 grams of sodium chloride, salt, and then it tells us that that's dissolved per 1 liter, per liter. Well, that means they gave us the volume of the solution. They gave us this down here. So if we need to figure out the molarity, and this is our main goal, to get molarity, we need moles of solute, which we don't have yet, and we need liters of solution, which we do have. So our goal is going to be to get, how do we get moles of solute from grams of solute, which is what we have, and then we'll plug that in there, divide by liters, and we're all done. It's a pretty quick problem. So we've got grams. We've got 28 grams of NaCl. We've got 1 liter of solution. Per liter means per 1 liter. So we need to get from grams to moles, convert, and then divide by 1 liter, and we'll have our answer. So let's do that together. 28 grams of NaCl. We need to convert that to moles. We haven't done that for a while, unless we've been working on some stoichiometry problems lately. But to convert to moles, remember, we just need a statement that relates moles of NaCl to grams of NaCl. And that's that molar mass. Remember, maybe it hasn't been a little while for some of you since we've used it, but that's our molar mass. And if you don't remember, that comes off the periodic table. We're just going to go add up Na and Cl, add up sodium and chloride off the periodic table. We'll get around 58.45 grams of NaCl. You can go add those up yourself, but I'm not going to pause very long in the video here for adding up molar masses. So if you want to go try those and make sure that you understand where those numbers are coming from, by all means you should do that. But if you trust me and you kind of get where those numbers are coming from, then feel free to just kind of whip along through these problems, and we'll get through a few more a little more quickly that way. What does this give us? 0.479 moles of NaCl. It didn't ask us for moles, it asked us for molarity. And so just to kind of take, we've got moles here of NaCl. Our equation, remember, is moles divided by liters gives us molarity. Moles divided by liters here gives us molarity. And so we have moles, 0.479. We have liters, that's 1. Well, that's pretty easy then. 0.479, oops, let's try that again with a pen, not with a highlighter. 0.479 moles divided by 1 liter of solution is going to give me a concentration of 0.479 moles per liter. You can write that as moles per liter, because those units don't cancel out, of NaCl. Or the short way we simply start to see us writing it more and more is moles per liter is molarity. We just write that as a capital M. And when you see it printed out in type, it'll usually be italicized and capitalized M. So this is 0.479 moles per liter of NaCl, or 0.479 capital italicized M for molarity. That's what the question's asking for. What is the molarity? And we've found that now. Easy as that. Let's do number 2. I'm going to clear off my little cheat sheet here so you can fill it in with information from the next problem as well. Okay. This question again asking, what is the molarity? So in the end, we need to figure this out. What is the molarity? Same as in the last one. To do that, we need moles of solute and we need liters of solution. What have we got? This question is telling us we have 5.3 grams of Na2CO3. That's my solute. How do I know that's my solute? Well, there's nowhere else in this equation for a mass to sneak in. That's one of the ways we know. So this must be grams of solute that they're giving me. It can't be grams of solution, because how the heck would I get that into this problem? But it also says right there in the verb in this question that the Na2CO3, the sodium carbonate, is dissolved in the solution. So that's the solute. Solutes are dissolved into solutions. They're dissolved in solvents to make solutions. And then we've got volume of solution here in milliliters. So let's take a look at that equation once more. We have grams of solute here, and we have milliliters of solution here. We're just going to need to convert both of those and put them into the places that we need them to be, which would be moles and liters. All right, so let's do that. 5.30 grams of Na2CO3. We're going to need to convert that to moles. Well, periodic table says that 1 mole of Na2CO3 has a mass of 105.99 grams. So that'll get us our molar mass to convert to moles. And if I divide that out and convert it over to moles, it's not very much. It's 0.0500 moles of Na2CO3. Right? Now, we've also got 400 milliliters of solution. 400 milliliters is not in liters, but we can make a quick metric conversion. And with all metric conversions in our class, you don't have to show work for a metric conversion. But if you'd like to, and you're a little more comfortable doing that way because you're worried you're going to mess up the decimal places or move them the wrong direction or something, 1 liter is 1,000 milliliters. So to get to liters, we're essentially dividing by 1,000, which means we've got 0.4 liters of solution. All I really did there was move the decimal over 3 places, but converting in decimal, or rather in the metric system, that's often what we're doing. So we have moles and we have liters. And according to my molarity equation, I need to take moles and I need to divide by liters. Put a dividing line, divisor, right between moles and liters, and I'm all set. So I'm going to put that in there right there. Moles divided by liters, and I'll have my answer. If I divide that out, 0.125 moles per liter, or just a capital italicized M, Na2CO3. Remember, whenever you see that capital italicized M, it means moles per liter, moles over liters. So there's my answer, 0.125 moles per liter, or the molarity of the solution will be 0.125. What is the molarity? We've got a molarity there as our answer. All right. I'm not going to do 3. I'll leave that one for you. All right. Let's take a look at number 4. Number 4 says how many moles of Na2CO3 are in 10 liters of a 2 capital M solution. Remember, what does that mean to us? Take a second there when you see that capital M. What does this mean? This means 2.0 moles per liter, per 1 liter. Whenever I see that capital italicized M, it means moles per liter. So there's actually 2 values there. It's moles, and it's kind of 2 moles per 1 liter. So whenever you see that, it's kind of like you have to peel that apart and recognize that that capital M actually holds within it sort of 2 units, moles and liters. That's important. All right. Let's go back to our equation here. What are they looking for? How many moles are in 10 liters of a 2 mole per liter solution? Well, in my equation, what are we talking about here? How many moles, that's that guy, are in 10 liters, so they've given me this, of a 2.0 molarity solution. So they've given me molarity, and they've given me liters, and they're asking me to find moles. Hey, that means I don't even have to worry about any of this stuff this time, right? That's not even going to come into play, because they gave me 2 of the 3 parts that are here in black, and those are like the core of this equation. If they give you 2 of those 3 parts and they ask you for the 3rd one, then you're done. You don't have to worry about those extensions, those green kind of extended parts off the side of the problem. We're just going to put it in this ratio and go for it. Okay. So moles, if you take a look at our equation here, moles of solute is on the top, molarity, and then liters will be on the bottom. So we can follow that sort of a pattern over here. Molarity is 2.0 molarity. The moles, how many moles? That's what they're asking me for. So I can put my X up there in the top. You can write it as X moles. You can write it as just X. And then the volume goes in the bottom. That's 10 liters. So my little equation here, I'm just following the guidelines of my main equation here in the black. Molarity equals moles over liters. And what we've filled in so far then is exactly that. Right? Molarity equals moles over liters. So those 3 parts just filling in their little places within the equation. So to solve, well, you can think about this as 2 over 1, right? That's kind of what it is. In fact, it's, like we said, 2 moles over 1 liter. And that'll help us to be able to do the cross multiplying. So by cross multiply, X equals 20, right? 2 times 10. And 20 is, and X is in the moles position. So 20 moles of Na2CO3. There's our answer. How do I know it's moles? Because what we were solving for was in the numerator. My X was up here in the numerator of the equation, and that's in the moles position. So the answer is going to come out in moles. Can I be even more sure of it than that? Absolutely. I'm just going to clean this out here. And remind us that when we cross-multiplied, we took 1 times x, well that's obviously x, and then we took 10 liters and 2 moles per liter and multiplied them together. So 2 moles per liter, and then we took that times 10 liters. And when we do that, the liters cancel out, right? And that leaves me with moles. So we can definitely see that the units do match up with the answer that we came up with, 20 moles of sodium carbonate in 10 liters of a 2 moles per liter solution. That one's pretty obvious, I think, if we look at it a little more closely with the math, but even just at a glance, that one's pretty straightforward. And very similarly in number 5, how many moles of NaCl are contained in 100 milliliters? I'm going to look at that right away and say, I don't like 100 milliliters here. I'm going to turn that into a liters of volume pretty much right away, because I know my main equation, and again, let's clean that up over here. My main equation needs me to have liters of solution, not milliliters. I can start with milliliters, but I've got to make a conversion to use it in the equation. So let's let the first thing that we do be that conversion. What's 100 milliliters converted into liters? Remember, you can do that conversion on paper, or you can just sort of do it in your head, as long as you do it right. That's the key. That's going to be 0.10 liters of solution. 100 milliliters or 1.1 liters. Okay. How many moles? Again, we're solving for the top value here. This is going to be my x. How many moles? Do I have molarity? You bet. I've got a 0.20 molar solution, 0.20 moles per liter solution in the problem. And now I've got my volume in liters for my bottom of the equation. So I've got molarity, I've got liters, I need moles. Same as last time, we're not going to even have to look at this part of the extended equation anymore. Okay? I shouldn't get quite so aggressive about it. We won't have to use this. We already did the conversion, right, from 100 milliliters to liters. We've already done that. That's what we did to get this. And our molarity is given to us at 0.20 moles per liter. So all we have left to do is find for x. So let's set that up over here. 0.20 moles per liter, or simply written 0.20 m in my molarity position, equals x moles, that's what we're trying to find, divided by 0.10 liters of solution. And again, we're simply going to cross multiply. X, when I cross multiply, will be 0.02 moles of what? NaCl. And there we go. Moles, how many moles? We figured out moles, and we're all done. All right. Let's jump down to number 7. I'm going to leave 6 to you. Let's take a look at number 7. How many grams of calcium hydroxide are needed to make 100 milliliters of a 0.25 moles per liter solution of calcium hydroxide? How many grams of calcium hydroxide? So if we look at our equation again, how many grams? They're asking me to find this guy out here, right? That's my goal. How many grams of calcium hydroxide? What have they given me? They've given me 100 milliliters. So that's down here, 100 milliliters. And they've also told me that it's a 0.250 molarity solution. So they've given me this, they've given me this, and they're asking us to find this one out here. Okay? So what we're going to do, you can kind of see this is almost like a little loop through this problem. We're going to have to take those milliliters and turn them into liters, plug it in there. And then we're going to have to use that in liters along with our given molarity to find moles, and then we'll convert to grams. So we're kind of working our way around this problem almost sort of in a big loop, okay? Sort of like that. Starting with milliliters and then working our way kind of like a boomerang through this problem, all right? So let's see if we can't do that. First, that 100 milliliters we need to convert to liters. Hey, we just did that in the last problem. So how about if we just take that answer from the last problem and we use it again? 100 milliliters is still 0.1 liters. All right? So again, once you get more comfortable with those conversions, don't feel like you have to write them out every time, but you can absolutely write them every time if you need to. So there's my volume. I know my molarity. I've got a 0.250 moles per liter solution, and I've got 0.1 liters of it. How many moles will that be, right? So remember, we've figured out here that this is 0.10 liters. We've got our molarity, we've got our liters. We're going to find that moles, and and then we're going to convert it to grams. All right, so that's where that x position is. When I multiply this out, x is 0.0250 moles of calcium hydroxide. Now in the last couple problems, that's where we would stop. All right, but we're going to go just a touch further because the question wants grams, not moles. And again, once we've got moles, as we do now here, we can go to grams by a conversion, and that's a mole conversion to grams, like we used in stoichiometry. So we're one more step away, and then we're going to be done. For 1 mole of calcium hydroxide, how many grams is that? We go to the periodic table, we add up calcium hydroxide. You can do that if you wish. You should get 74.09 grams of calcium hydroxide makes 1 mole. And if you multiply that out, moles will cancel moles, and we'll have grams, right? Take a moment if you need to with your calculator, or if you want to just trust me here, 1.85 grams of calcium hydroxide would be needed to prepare the solution they're describing. So we converted from milliliters to liters, right? That was our first step. We made that metric conversion. Then we used our main equation here to find x in moles. And we got that value here. And then we converted that using a molar mass, remember from the periodic table, to get into grams that are equivalent to that moles. We can't go in the lab and measure out 0.025 moles. We don't have a molometer back there. But we can convert to grams, and we can easily go to the balance and measure out 1.85 grams of calcium hydroxide. Lickety split. All right. One more problem I'd like to do with you, and that's question number 10. 8 and 9 are a lot like 7, so I'll let you work on those. Number 10, what volume in milliliters is needed? What volume in milliliters of this solution, and there's a bunch more details here, is needed. But before we get into those details, what are they asking me for here now? Well, it's this one right down here, right? They're asking me to find this. I'm going to put that in blue. So help it stand out a little bit. This is what they want me to have. Milliliters of solution. How many milliliters, okay, would be needed? Of 18 moles per liter H2SO4. So they're giving me the molarity is 18 moles per liter. So they're giving me this. What else? They're giving me 2.45 grams of H2SO4. And again, grams only have one place here. Goes right up here. They've given me this, 2.45 grams. So they're going to ask me to get from grams all the way down here to milliliters of solution. It's kind of the reverse of what we just did, right, in the last problem. Because we're going to start with grams, whip our way around through the problem this way. I'm going to convert from grams of solute into moles. Then I'm going to use moles along with molarity to get liters. And then we'll use liters to convert this way down here to milliliters at the end. So it's a 3-step problem. And you kind of imagine then, convert, use the main equation in black, and then convert again to get down to milliliters of solution. So our first step here is to go from grams into moles. Our first step is a gram-mole conversion. So let's go back and do that one first. All right, 2.45 grams of H2SO4. To convert that to moles, we're going to do the same thing that we did in the very first problem that we did together. We're going to look up the molar mass of sulfuric acid on the periodic table, add things up, and you can add it up. It's 98.08 grams of H2SO4 for every mole of H2SO4. All right, and if we multiply that out, grams will cancel grams. I actually should say if we divide that out, because 2.45 times 1 divided by 98.08 is what we're needing to do here. That gives us an answer of 0.0250 moles of H2SO4. So we've got moles. Where do we go from there? Go back to my equation. I've got moles now. What do we say? 0.025. 0.0250 moles. So we've gone from milliliters, we've gone from grams to moles. Now we've got moles and we've got molarity. So we've got moles and we've got molarity here. Now we're going to solve for those liters of solution. We're just working our way through, filling in all the spaces actually by the time that we're done. Let's figure out the liters of solution in the bottom here, all right, using those moles. So my equation says, 18 moles per liter, or 18 molar, is 0.025 moles, which we just figured out. And then on the bottom, I've got how many liters. That's what we're looking for, right? That's my denominator. How many liters will that be? All right, if we cross multiply and divide here, take your time with this. Okay? When the x is in the denominators, when we see a lot of students make frustrating mistakes. Okay, if we cross multiply here, what do we have? I'm going to be simplified and not going to worry much with units at this point. I know that x is going to be down here. It's going to be liters. So whatever my answer comes out to be is going to be liters. So I'm going to leave the units off just to make our lives a little more clear at this point. 18 times x is going to be 18x. 1 times 0.025 is going to be 0.025. Divide both sides by 18. Be careful with your algebra. Don't just assume you know what you're doing unless you do. Okay. And when I solve that, x comes out to be how many liters? 0.00139 liters. Okay. So that was x in the liters position, denominator of my ratio over there. Okay. Is that the answer? The question says what volume in milliliters. So we just need to go one step further because we've solved for liters. All right, we're down here, 0.00139 liters. We need to get to milliliters, and that's that metric conversion. To get from liters to milliliters, it's simply a matter of 1 liter is 1,000 milliliters. So we take that times 1,000, and our answer is 1.39 milliliters of solution that we would need to accomplish what they asked us to there on that question. All right, so we've worked through 6 of the problems in this assignment. There are a total of 14, and none of the ones that are left are any different than the ones that we've already done together. You just have to use those kind of as your background to be able to work through the other ones that we've left for you. All right, so take some time with these, use the examples, use the equation, watch your units so that they cancel out properly and that you know where you're going. So start out with a little road map over here and map it out however many times you have to. It's not a race. Much better to take your time and get it correct than to get it done quickly but be wrong. All right. Hope this video helps. Work on these and check that due date so you know when to have your answers posted on Google Classroom. See me in office hours if you have questions, and we'll talk to you then. Thanks.